Okay, you're given this function f of x equals the log of the quantity x squared plus 6 and asked to identify the intervals of concavity and the points of inflection. Okay, so I did this for any base b. Turns out the points of inflection and the intervals of concavity will be the same regardless of whether this is a common logarithm base 10 or natural logarithm base e or any other base. Okay, so this right here, this black graph is the graph of the function. The blue graph is the first derivative. Notice that the first derivative changes sign when x is 0. It goes from negative to positive, and this function goes from decreasing to increasing at 0. And the second derivative, which is the green graph, has a value of 0 at the square root of 6 and at the negative square root of 6. And that's where the points of inflection are, because the second derivative changed sign. It went from negative, which you can barely tell, to positive, and then back to negative. Now, so these are the points of inflection right here, the square root of 6 and f of the square root of 6. And negative square root of 6 and f of negative square root of 6. Okay, and these are the first and second derivatives instead of using the Desmos prime notation. So let's see how we did that. You want to find f prime of x, where this is the base, b. Derivative of a logarithmic function is 1 over the parameter of the logarithmic function times, in this case, the chain rule, the derivative of the parameter, which is 2x. And then for base b, you have to multiply by 1 over the natural log of the base b. Notice that when this is really an e, ln of e is 1, so this part disappears. But for any other base, you have to keep that if you want the correct form for the derivative. So there's the first derivative right there. Now, how do you find the second derivative? Well, I kind of think I'm going to take 1 over ln of b times the derivative of this thing using the quotient rule. And there's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. Remove parentheses, combine similar terms, you get negative 2x squared plus 12. So to find the points of concavity, we want to know when does the second derivative equal 0. So we set this equal to 0. This will only equal 0 when this numerator is 0. You can say, well, I'm going to multiply both sides by ln of b times x squared plus 6, the quantity squared. You'll still get a 0 over here. So there's how you find out the values of x where the second derivative is equal to 0. And then you apply the concavity test. So what's the sign of the second derivative to the left of the negative square root of 6? Plug in a number like negative 3. And you can see that this factor right here is always positive. Well, I should say it's always positive if the base is greater than 1. But if I put a negative 3 in here, I get a negative for this term that's greater than 12. And so that's negative. And when the second derivative is negative, the original function is concave downward. If I try 0, a number between negative square root of 6 and square root of 6, I get a positive. Positive, think smiley face. Negative, think frown. There are the points of concavity right there. And that means it's concave up from negative radical 6 to, it's concave up from negative radical 6 to the square root of 6, and concave down on these intervals right there. Okay. And of course, if you actually had to find the points of inflection, you'd have to take this number and plug it into the original function. So it'd be the log of square root of 6 square root of 6. 6 plus 6 is 12. So it'd be negative square root of 6, comma, log of 12. There you go. Hope that helped. If you have any questions, post a comment.